recording. You're good to go.
Okay. So,
I'm here.
okay.
Yeah, perfect. Go.
Cool. Thank you. So as Daniel said, I will start exactly where we finished the last time. So, remember, last time we finished exactly by constructing the free part of the string field theory action, that is the kinetic term, right? I gave you this nice general algebraic form, and then I also went through a couple of examples. So for an open string propagating on a 25 brane in flat space. So the point of today's lecture will be mainly to see how this kinetic term, how this free action gets extended to also include all the possible interactions, right? Because without the interactions, we are basically not able to do anything else just than to encode the spectrum of the string propagating on a given background. But if you want to compute anything more complicated, like amplitudes or some non-perturbative effects, we certainly need to know about the string interactions. Right?
Is there any mapping between the interactions and the background?
Well, yeah. So in order to
understandable, easy, I imagine there is, of course. But
right. So in order to be able to write down the action, even at the free level, as we were discussing last time, you need to assume that you know the worksheet background, right? That you know the worksheet CFT, right? And then this what we started calling dynamical string field phi is nothing but a linear combination of states in the Hilbert space of the worksheet CFT, right? In this particular case, it's a particular class of states which arise at a ghost number 1 in the open string case and a ghost number 2 in the closed string case, which in this unified language of using this degree was at degree 2, right? So that is the dynamical string field. It's just a generic element in the string open space, right? So then of course we will see that in the language of SFT, different backgrounds can be seen as classical solutions of equations of motion, which are derived from this action. So that will be one of the messages which I'll try to convey also today. But then continuing in the recap, we saw that if we just focus on this kinetic term, right? When we vary, we derive an equation of motion, which is precisely equivalent to the statement that the state is physical. It's BRST closed, right? That it's an element in BRST cohomology, right? And the freedom in shifting the state by BRST exact state, right, was precisely reflected by the fact that this kinetic term enjoys a gauge symmetry under gauge transformation, which is precisely a shift of the string field by something Q exact, where lambda was yet another string field, this time arising at degree +1, which plays the role of the gauge parameter.
Can I ask a question?
Yes.
Is there some natural real structure on this Hilbert space?
Which structure?
Real structure.
Real. What do you mean by real structure?
Well, so it's a complex vector space, right? Complex numbers.
Yes.
But then when you write a physical state, like for example the gauge boson,
Yes.
the gauge connection is real.
Yes.
So how do you get? I mean, how do you get it constrained? Why can the connection be complex?
Yeah. Okay. So the important requirement is that after you substitute for the string field, right? So the string field is, in general, there are non-compact directions. String field is an integral of the momenta, right? And the moment representation with some coefficients, right, which play the role of the Fourier jewels of the space-time string fields. So then the important requirement is that the action which you end up with is real, right, as you would have expected in any field theory. So in that sense, there is a real structure. Okay. I think it can be formalized, also in terms of a statement at this level. I just didn't think about it. We can maybe think about it later. Okay. So then, given this intro, we will spend the rest of the lecture trying to build these interaction vertices. In particular, I will try and derive some nice algebraic structure which these vertices have to satisfy in order for this action to be quote-unquote consistent. So now, of course, I have to tell you what I mean by this action being consistent. And this is the basic requirement which goes into the construction of these vertices. And that is that this action needs to be built in such a way so that when we then use the Feynman rules, which are encoded in that action, we need to recover what we call offshore string amplitudes. Right. So now I will spend some time trying to introduce at least roughly what these offshore string amplitudes are. And for the sake of definiteness and also actually simplicity, I will focus on just the case of the closed strings. So then the result for the open strings I will comment on later in the lecture, and we derived in pretty much a similar way. There is just some additional structure which I didn't want to bother with at this kind of first explanation. So starting with the notion of the offshore string amplitudes, let me first tell you schematically what they look like. So of course, I mean, they are what you would have expected. I mean, they're supposed to be some sort of offshore generalization of onshore string amplitudes. So very, very schematically, in the case of onshore string amplitudes, of course, you remember, well, the task you have to do, you have to take your favorite Riemann surface, which is supposed to represent the particular element of string perturbation expansion which you want to compute, right? So it usually works at some definite genus and definite number of external punctures. So in this case, since we will not want to be bothered by loop effects, at least at this first level of explanation, I will just consider Riemann surfaces with a genus 0. So this is why I'm putting the 0 here, and punctures which are supposed to represent n external states. Right. So in the case of onshore string amplitudes, I'm supposed to take this Riemann surface, and at each of the punctures I'm supposed to insert a physical string state, which, as we discussed last time, can be always represented using a state in the worksheet CFT, which has total worksheet dimension 0. So actually, not just the total dimension 0, but since the state needs to be level matched, also the left and right moving conformal dimension 0, right? So now, in that case, it doesn't really matter what kind of local coordinates I choose on the surface, right? Because since the state has dimension 0, 0, right, I can always act on it with any locally with any conformal transformation, and the whole correlation function needs to stay invariant, right? As long as this is dimension 0, 0 primary, which is always the case for these physical states. Now, if we want to generalize these onshore amplitudes to a generic offshore insertion, where the state is allowed to have generic dimensions, h and h bar, as long as they're level matched, right? This is now as good as saying that the answer is no longer going to be invariant, under changing local coordinates. So I always have to make a choice of local coordinates around each puncture. So these in this picture are represented by these functions fi of wi, well, where z I don't know to be this kind of coordinate on the on this Riemann surface sigma 0 n, and wi are the coordinates on these local patches which map a unit disk from this wi complex plane to a disk-like region neighborhood around each puncture of the Riemann surface. So for each puncture where I'm inserting the external state, I have to make a choice of the local coordinates. So that's one ingredient which I need to assume for the computation of these offshore amplitudes. And then the integrand, roughly speaking, of the offshore amplitude would have been given just as a correlation function in the worksheet CFT on this Riemann surface sigma 0 n of this schematic for, right? Where I'm inserting each state, each offshore state at the origin of this local coordinate system, and I'm mapping it with this function f of I to the Riemann surface. But now, of course, there is something more to this, right? Even in the case of the onshore amplitudes, what I then have to do, I have to integrate over the moduli space of this Riemann surface, right? So usually this is, I mean, even at genus 0, there is a non-trivial moduli space which is connected with the choice of the positions of the punctures on the Riemann sphere, right? That's that's one thing which I have to do, and then of course I have to choose a suitable measure for this integration, which is also very tightly connected to the fact that in this correlation function I also have to insert some contour integrals of B ghosts, right? So if you remember last time when we talked about the BCFT, we have seen that in order for this correlation function to be non-zero, I need to saturate the ghost number to be +6 in the ghost string case, or +3 in the open string case, right? So the non-trivial correlator holomorphically will C for the C ghost, right? So now, if each of these external punctures is supposed to be represented by the state phi at ghost number 2 in the ghost string case. Now, of course, if there is generic number of punctures equal to n, right? Then I need to compensate. I mean, the ghost number coming from just these phi insertions would be n, right? So in order to get down to 3, I need to compensate by a suitable number of B ghost insertions. So this is the meaning of this. So these are schematically some B ghost contours, right, which will be functionals of the coordinates ui on the moduli space, which very simply you can think of as the position of the external punctures, and these contours are to be inserted inside this correlation function. Right. So then, of course, we in the case of onshore string amplitudes, we are integrating just over the moduli space of the Riemann surface. So now, in the case of the offshore amplitudes, things get a little bit more complicated, right? Because not only we have to compute this correlation function and different points of the moduli of the Riemann surface, we are also making this choice of the local coordinates around each of the punctures at each point of the moduli space. So if you think about this geometrically, that amounts to saying that I have this fiber bundle, right, where the base of the fiber bundle is just the moduli space of punctured Riemann surfaces, and at each point of this base, I'm constructing this fiber, which corresponds to the freedom of choice of these local coordinates. In total, I'm getting this fiber bundle PG and hat, right? Where this hat is due to the subtlety that which I have not mentioned so far, and that is that each of these local coordinates they can be chosen only up to phase, and this is basically due to the fact that since the states which are to be inserted at each puncture, although being generically offshore, they still need to be level matched. Since they are level matched, they need to be killed by L0 minus L0 bar, the spin in the worksheet CFT, and that is they are not going to be sensitive to the redefinition of the local coordinates by a phase, right? Yeah, in principle, I have this freedom of choosing the local coordinates only up to a phase at each puncture. So then, since I'm making a definite choice of the local coordinates at each point of the moduli space, this amounts to making a choice of a section of this fiber bundle, and this section is something which I call this FGN. So this is morally speaking the correct thing to be integrating over in this offshore amplitude. Okay. So this is a very schematic picture of what an offshore amplitude is. So now let me give you somewhat more formal definition. For instance, I didn't tell you what these B ghost contours as functionals of these coordinates on the moduli space should be. So so they have to be chosen in precisely such a way so that the offshore amplitude satisfies some formal requirements. And these are as follows. First of all, I want to write the offshore amplitude as an integral over this section f0n. And of course, in order for this integral to have an invariant notion, which is independent of the choice of the coordinates on the moduli space, what I need to be integrating over is a P form, right? And the P form and the rank of the P form, P needs to be precisely the same as the dimension of this space of this section f0n. So then, of course, I can talk what are the properties of this form which I'm integrating over. So at the level of this picture, the form will be everything inside this correlation function. So it will be constructed out of these correlation functions on this surface sigma 0 n, and also it contains this definition of the measure and the B ghost contours. So then, of course, I need to choose this form in such a way so that this offshore amplitude, when I take these external states back on shell back to be physical, I need to be able to recover the expected answer for the onshore amplitude, right? So then, second, since I can always apply a global conformal map to permute the punctures on the Riemann surface in any way I like, I need to ensure that the total offshore amplitude is totally graded symmetric with respect to the insertions of these states phi 1 dot phi n, right? So that needs to be also reflected at the level of this integrand of this P form. So I need to require that this P form is totally graded symmetric in these phis. And the final property, which needs to be satisfied, is motivated by the fact that when I reduce everything back on shell, I need to ensure that if I happen to insert a state which is zero in the cohomology, but not represented by a zero state, that is represented by something which is BRST exact, that answer is zero. That is, the BRST exact stays decoupled when everything is taken on shell, right? So
the cohomology only makes sense on the weight zero objects, or is there a notion of this cohomology on the whole space of offshell states, or what's it?
Well,
is it logical or
yeah, you will see that at the level of the offshell states where I also add the interactions. The notion of the cohomology needs to be generalized to a more general gauge transformation. So as you will see, the algebraic structure of these vertices which I was talking about will happen to be that of the L infinity algebra, right? And of course that will also generalize the notion of the gauge transformation. So the gauge symmetry of the full interacting action will no longer be just Q lambda, but it will be corrected by some interactions, right? So this is the correct generalization of the notion of the RST exactness.
Yeah, I should say I'm a little bit lost in the global logic of what is happening. So is what is happening now? You're explaining how to fix the V ends, or yes. Are we assuming that we already okay? Yeah.
Yes. Okay. So okay. Yeah. Okay. Just to repeat what the global logic is, we are attempting to fix the V ends in such a way so that the Feynman rules reproduce the offshore amplitudes, right? So now I'm explaining what an offshore amplitude is, and in a second I will actually take this offshore amplitude and try and reinterpret it as a sum over Feynman diagrams, right? And that reinterpretation will tell me what the vertices have to be.
So to uniquely fix the VNs, it is important to consider offshore amplitude, because I would somehow think that a string theory is more, at least perturbative string theory is uniquely fixed by the onshore amplitudes.
Well, perturbative onshore amplitudes are, yeah, okay, yes. These are unique, but we are not attempting to fix VNs uniquely. There, as you will see, there is a huge non-uniqueness in these VNs, right? Because at the level of an offshore action, you can always make a filter definition, right? So that filter definition should not affect, any notion of consistency of the action which you're trying to use, right? And indeed, I mean, as we were seeing here, I mean, there was a huge non-uniqueness even at the level of defining of what an offshore amplitude is. Offshore amplitude is not an observable object, right? Because there is a huge, freedom of choice of this section. I mean, we can choose. I mean, we can choose the local coordinates at the punctures in basically anywhere you like, right? So an offshore amplitude is not an observable object, and that non-uniqueness in the choice of the section will be one of the factors which goes into, which is connected to the non-uniqueness of the action, through the freedom of making a filter definition.
Because before this course, my understanding was that there is a particular string theory which computes onshore amplitudes, and then we can upgrade this to a string field theory by taking this input of the onshore amplitudes, and then we use string field theory to compute the offshore amplitudes.
No.
What you're saying, we need some extra input to even define what string field theory is.
Exactly. Yes. Yeah. And then whatever observable we compute with string field theory. If the observable is to be, associated with an onshore amplitude, that needs to match with whatever prediction we have from the worksheets, right? So that's the logic. Okay. So in particular, we need to ensure that these offshore amplitudes are defined in such a way so that when we go on shell, the BRST exact stays decoupled, right? So that is ensured by requiring this strip property, and that can be summarized basically by saying that if we act with Q on the states inside this integrand P form omega, that is as good as acting with an exterior derivative on a form with full rank, right? So in order to see how this works, let me actually show you. So let me assume that I want to compute an onshore amplitude using this prescription. So I'm integrating over epsilon this form to omega 2 n minus 3. So 2 times n minus 3 is precisely the dimension of the moduli space. Is the real dimension of the moduli space of n punctured Riemann spheres. That you can check. If you substitute n equal 4, right, that's the form function sphere, you get 2 times 1, which is 2, which is precisely the right answer. 0 n. And now let's do what I was suggesting. Let's try and insert a state which is manifestly BRST exact, and let's assume that the rest of the insertions are physical states. So then, of course, since rest of these insertions are physical, right, you can see that the only contribution to the left-hand side of this relation comes from the first term, right, from this Q lambda, right? Then in the other terms, there is Q acting on the other insertions, but these contributions are all 0 because I'm assuming that these states are physical, so they will be killed by Q, right? So this is directly equal to whatever we have on the right-hand side. So we have an integral of 0 n. The sign is not very important because we want to get a 0. So then so we got something which is exact on the integral, so we can use the Stokes theorem to rewrite it as an integral over the boundary of the space n0 n. So now you have to think what the boundary of the space looks like. In particular, what are the Riemann surfaces? which populate the boundary of the moduli space. So these are precisely the surfaces which contain at least one degeneration, right? So these are precisely surfaces of the type which we were drawing a lot in the first lecture, where this pinch of the Riemann sphere should be thought of as taking the original Riemann sphere and decomposing into two Riemann spheres which are connected by a very, very long thin closed string tube. So this is a tube-like region connecting the two spheres. Okay. And in a moment we will try and reinterpret it as a very, very long propagator, right, in the language of Feynman diagrams. So now this piece of the worksheet, this tube, can be generated by inserting an operator e to the minus t L0 plus L0 bar, right? So as we will see in a moment, this will indeed turn out to be a contributing piece into the closed string propagator. And now the boundary is going to be obtained in the limit where t goes to infinity, right? So you can see that inserting such an operator in any correlator in the limit t goes to infinity is as good as projecting any states which are propagating here to lie in the kernel of that guy, right? Right, because as soon as the eigenvalue of L0 plus L0 bar is non-zero, that operator would project everything else, right? Because it would just go to zero. So,
unless there are negative eigenvalues?
Unless there are negative eigenvalues, which can happen in bosonic string theory, but these can be made sense of using canonical continuation. Okay? So, yeah. So at the boundary of the space, we are projecting the states propagating in this intermediate channel to be in the kernel of L0. But for generic external momenta k1, k2, kn, right? You can easily argue that this generically does not happen. This would only happen for very, very special fine-tuned configurations of momenta. So generically, this thing is zero. Right? So this is what we wanted to show. So this was just to illustrate how these algebraic requirements give us what we expect for the on-shell amplitudes. So now, as I was promising, we want to build the vertices of our SFT in such a way so that the Feynman rules of the action will precisely reproduce these off-shell amplitudes, right? So for that, we need to take this result for the off-shell amplitude and reinterpret it as a sum over Feynman diagrams. So we are kind of building the action from the bottom up. Okay. So this is our task now. We will try and decompose the space F0n into some subregions. And the first class of subregions are the elementary vertices. So these are the elementary vertex regions. Which I'm going to denote as V0n.
F0n is the whole space, the moduli space plus the choice of local coordinates, or this
F0n is the section. Is the section.
Oh, is this, okay, yeah, it's what you draw.
Yeah, it's the section. Here I draw it. So this V0n is a subspace of F0n, such that when I restrict this integral, which comes into the computation of the off-shell amplitude just to the space V0n, we will precisely obtain the vertices which go into the action. So these Vn's are the same Vn's as I was writing down just at the start of the lecture. And as I was saying, these are computed by restricting the integral to just V0n. And at the level of the Feynman diagrams, these are to be interpreted as elementary vertices. So now, of course, you can never hope to cover the whole space F0n by just these elementary vertices. So the second kind of region into which we need to decompose the space F0n will be precisely the regions which are covered by the propagators, and these we call the Feynman regions. So these will be covered by elementary vertices V0m, where m is strictly less than n, so vertices of lower order than the number of punctures of the amplitude which we are trying to compute, plus propagators. So in order to be able to think quantitatively, let me first of all talk about the propagators. So the propagators, those can be of course constructed without even having a notion of interactions, right? I mean, using the common OR, a propagator should be something which inverts the kinetic operator of the action, right? So in string field theory, even at a free level is a gauge theory. In order to construct a propagator, I first of all need to fix the gauge. And why not fix our favorite Siegel gauge, which we already discussed last time? So we'll be assuming that these offshore states that are killed by B0 plus, or B0 plus was just B0 plus B0 bar in the Siegel gauge. And in this Siegel gauge, I will show in a moment that a propagator can be represented by this following operator in the Hilbert space, which I will call H. And it's precisely 1 over L0 plus times B0 plus. And this 1 over L0, it is also very convenient to think of it in terms of a Schwinger integral. So that's an integral over T, e to the minus T, L0 plus L0 bar. So this is precisely the exponential which was appearing on the previous board, and B0 plus. Okay. So now let me convince you that this operator actually precisely does what we need it to do, and that is it inverts the kinetic operator. So the kinetic operator of the SFT is just the BRST operator. So what we need to prove is that when I act with H on Q phi, where phi is generic state, in a Siegel gauge, I will get just phi, right? So let's do that. So first of all, let me notice that since this state phi is in Siegel gauge, I can rewrite this HQ as H anticommutator Q. So again, this is going to be a graded commutator. In this case, since both H and Q are Grassmann odd, right, because the ghost number of H is -1, this is really an anticommutator. So why is this true, right? Just think of the other side of the anticommutator, that would be H hitting directly phi, right? But that is as good as B0 plus hitting the phi. So that is 0 by the Siegel gauge condition, okay? So then we have to think what this H is, right? So we know that by definition H0 is 1 over L0 plus Q B0 plus, right? For L0 plus, we know that it commutes with B0 plus, right? That you can just very quickly verify. So this 1 over L0 plus can be taken outside. Then we get the commutator or anticommutator of Q with B0 plus, and that we saw last time that it was equal to L0 plus. So indeed, we get just the identity.
In principle, if we just go back to the origin of free action and derive the propagators from it, right?
That is what I effectively.
It's equivalent. It's equivalent. This is like a compact way to do it for all fields at once.
Exactly. Yeah. I guess what I'm suggesting, we could just break level by level. Derive a propagator for the tachyon.
I'm a down-to-earth person, so.
Yeah. So let me actually go precisely in this direction a little bit, and just mention in passing that for backgrounds where there were at least some non-compact directions, where we could have really propagating strings along some non-compact flat directions, we were observing last time that the action of L0 plus amounts to acting with k squared plus m squared, right? Where m squared was where m was the mass of the state, right? So that means that for such backgrounds, we can rewrite the propagator as 1 over k squared plus m squared b0 plus. So up to this b0 plus, this is precisely what we would have expected, from a propagator in a field theory. So now, having discussed the propagator, let me come back to our effort of trying to recast the offshore amplitude in terms of Feynman diagrams. So we have seen what the fundamental vertices are. So now we want to cover the rest of the space F0n by diagrams containing at least one propagator. So these are diagrams of that type. So as I was promising, those will be diagrams composed of 2 elementary vertices, where each of the elementary vertices is of the order, it contains a number of external punctures which is strictly less than n. So these are some, let's say, vertices V0R and V0, and then we need n minus r plus 2 in order to get n external punctures in total. So then phi 1, phi now r minus 1, right? Because the r function needs to, r of external state needs to go into the propagator, and then phi r phi n. So now the task should be to try and represent this diagram, try and implement the Feynman rules using these vertices, right? So at this point, I still don't know what these vertices are, right? But the logic should be that I'm now trying to derive an algebraic relation for vertices, which should be equivalent to the fact that I'm uniquely that I'm completely covering the moduli space of the offshore amplitude by this Feynman diagram expansion.
What about diagrams with more than one propagator?
Oh, yeah, of course, I will need to worry about them as well. For the moment, okay, let me just worry about diagrams with one propagator. And of course, there are many more than these, right? I mean, I can also choose to distribute the external states in a different way, and that way I will obtain different channels, right? So, yeah. So there. So now let me just take this particular Feynman diagram, and let me try and write an expression for it. Right? So I have 2 elementary vertices. Okay, let me actually start from the inside. So first of all, I have this vertex on the left-hand side, V0R, phi 1, phi r minus 1. And then the final puncture of that vertex I need to reserve for the insertion of this end of the propagator. So let me just write down the expression and then I will explain, or at least try to explain. So the insertion of the propagator I'm going to implement by an insertion of a complete set of states. And these complete set of states are, or the spaces is going to be represented by these states solidify alpha. So then for the other vertex, I need to reconnect it to the first vertex by this basis state phi alpha, phi r, and then the phi n. And then, just to emphasize that I'm summing over a complete set of state, just explicitly write down the sum over alpha. So these basis states phi alpha, they are chosen so as to be orthonormal just for the sake of completeness. Orthonormal with respect to the symplectic form, with respect to this non-degenerate bilinear from omega, which is given the action. So this is how this particular diagram would be evaluated using the vertices of the action. Right. So then, as Dana was pointing out, in order to reconstruct the complete offshore amplitude, I would not only have to consider different channels of this case with one single propagator, but then also there would be all the other diagrams containing more propagators, which would be corresponding to decomposing these vertices here. Again, these would correspond into resolving these vertices into more complicated subdiagrams, right? But
isn't there some tension between what you're doing and like the usual fact that what people usually say in string theory that the amplitude is either a sum of s-channel poles or the t-channel poles, but we shouldn't sum over like s plus t?
Yeah, but no, we are not sum. Okay. This. Think of it as decomposing this space f0n into regions which correspond to elementary vertices, which are regions deep inside the middle of the moduli space, right? And then towards the boundaries, you can start clearly saying that some of the diagrams they resemble s-channel, and some of the diagrams correspond to t-channel, right? So the trick is to choose a decomposition of non-overlapping regions of this f0n, where you can reinterpret the Riemann surface as coming close to degeneration.
Can we do some simple? Can we explain what happens for the 4-point?
Yeah. Okay. I will try to explain. I didn't really prepare it, but let me.
Because this is like all very abstract, and I don't really I don't understand what is the input and what is the output.
So for the 4 points, right? The moduli space is created by fixing 3 of the punctures and integrating over the position of the 4th puncture, right? So let me represent the moduli space, since we have 2 real dimensions. So 1 complex dimension, so the moduli space can be represented by a complex plane, right? Let me denote the position of this 4th puncture as u and u bar. This will be 0, this will be 1, this will be infinity, for instance. So then, in this moduli space, I will have 3 special points, right? I will have point 0, right? Where this puncture approaches the 0 puncture, and I will have point at 1. Where this puncture approaches the puncture at 1, right? And then I will have a point at infinity, right? So, depending on how I name the channels, I can, for instance, choose that when the moving puncture collides with 0, I will call it an S channel, right? So some finite region, right, around the 0, I will call S channel, right? Then again, there will be a finite region around this puncture 1, which I will call the T channel, right? And then there is going to be some region around the puncture at infinity, which I will call the U channel. S, E, and U. But in general, there is going to be a gap in between those channels, and that is precisely the region which needs to be covered by this elementary.
And the shape of this region is up to the string field theories that's constructing the action, or
exactly. That's yet another freedom which goes into the constructing the action, right? And again, together with the freedom of choosing this section, that will go precisely into the freedom of making a future definition at all levels of T. Okay?
Somehow I was. I understand what I misunderstood. Somehow I was assuming that somehow you were going to say that the contribution of the exchange diagrams to the 4-point functions, the external exchange diagrams would be the same as it would be in quantum field theory, but it's not, right? Because in quantum field theory we would integrate over. Yeah. Okay. No, I think I can't formulate confusion.
But thanks a lot for this question, which and for forcing me to draw this picture. That I think is helpful. So then, the basic requirement which should go into construction of these vertices is that this Feynman diagram decomposition, which I was trying to sketch, exactly covers this space F0. Right? So we need to cover F0n exactly once, with no gaps and no overcounting, right? So whatever was missed by these Feynman regions in that particular picture, exactly that I need to cover by the elementary vertex V04 in that case, right? So let's think about what this statement means. So that means that the boundary of the elementary vertex region so del is just the boundary operator here, right? Needs to precisely agree with the boundary of the Feynman region with one propagator in the limits where the length, where the Schwinger parameter of these propagators goes to 0, right? So this is precisely the statement about these curves in this picture, right? So perhaps I can make them blue. So this is the statement that the boundary of the elementary vertex region, which is whatever I'm drawing with blue now, needs to precisely agree with the boundary of these three Feynman regions. Okay, so these are precisely the loci in the moduli space where the propagator associated with each of these Feynman regions goes to where the length of the propagator goes to 0, right? So this is of course a correct statement even in the case of the more punctures. In the case of the 4 punctures, of course, I was able to cover the whole moduli space either with elementary vertex or with diagrams with just single propagator. In general, I will also need to consider diagrams with more propagators, right? But those will be then represented by different boundaries. So this is a nice and recursive statement which can be applied to each of these spaces V0 and separately, right?
I think I understand a little bit better what I was confused by.
Yes.
So, well, I guess when in the moduli space of Riemann surfaces, when you close Riemann surface, when you have a long tube forming, then this tube is responsible for one complex dimension of the moduli space, right?
Exactly. Yes.
But it looks like in your propagator there is only one real integration. So like you're trading this parameter. This one complex, so 2 real parameters, you're replacing it by one real parameter. You're integrating over this.
There is one complex parameter which is hidden, which I didn't really talk about, and that is an integral over an angle, which enforces the level matching condition, right? So what I'm really inserting inside the amplitude is this times an integral over the theta from 0 to 2 pi e to the minus theta L0 minus. Okay? And that accounts for the other dimension. Okay. So now, again, thinking about everything carefully, these two statements are exactly equivalent. Covering of the space F0n exactly once with these Feynman diagrams amounts to identifying the boundaries of the elementary vertices with the boundaries of these Feynman regions where these propagators become short. And that is precisely equivalent to what we call the geometric BV master equation. So at this point, think about this just as a name. Maybe if I have time, I will try and make a connection to the BV formalism later. So this is saying that the boundary of this space V0n pass the following, which I will explain in a second. Is going to be equal to 0. So now I need to explain what this operator curly brackets is doing to these spaces or to these subspaces of F0n. So it is doing precisely this, right? So when this long co-string tube, which is representing the propagator, gets to 0 length, what this amounts to? That is amounting to taking the two spheres, which are representing the two elementary vertices going into the diagram, and gluing these two spheres along a disk-like region. So this is the case where the propagator is still finite, still has a finite length t, right? So now when t goes to 0, this becomes an operation of, let me draw this somehow, of taking the two spheres and gluing them through this disk-like region around this puncture. So that is the same as saying take the two spheres and identify the two local coordinates around the two respective punctures. So this is precisely what we mean by this. So this then can be promoted to a well-defined operation on the space of surfaces, which is precisely what we mean by this curly bracket. So this is an operation of sewing, of taking a surface from each of these two spaces and sewing these two surfaces along these two disk-like regions, right? And that gives us another surface, right? And the space of these surfaces is precisely the space represented by these curly brackets. So that is an operation on spaces of surfaces, which gives us another space of surfaces, which is good, right? Because this is yet another space of surfaces, right? So and since those are precisely the surfaces which populate this boundary of the Feynman region described here, this statement exactly translates to this statement which I was making before. Up to this sign, so this sign is mostly convention and is due to the opposite orientation of these boundaries of the respective spaces. So this is how the requirement that we cover the space exactly once, this space F0n, translates to what we call a geometric PV master equation. So let me just make a few remarks. So the main remark is that this actually, if you stare at this equation, this defines a recursive procedure for constructing these vertex regions, right? So the recursion at free level starts by making an arbitrary choice of V03. So we pick V03. So that is just a cubic vertex, right? And that amounts to saying that we just choose suitable local coordinates around each of the punctures of the free punctured sphere, so that the vertex is totally symmetric in the states. But since we know that that this is a zero-dimensional moduli space, I mean, that should just amount to making a choice. And then the geometric BB master equation tells us that in order to find V04, we have to solve an equation boundary of V04 equals half bracket V03, V03. And then, of course, we can continue recursively. V05 will be defined in terms of V03, V04, etc., etc. So now, of course, in principle, this is an equation to solve. It is a generally a hard equation, and also at this level, it is a very abstract equation. It is just a statement on the spaces of surfaces. So, in order to translate it into something more computable, let us remember this one particular property of the offshore amplitudes, right? So we were saying that inserting the BIST charge Q inside an offshore amplitude was as good as saying that we act with an exterior derivative on the P form defining the offshore amplitude, and then upon integration over this FGN was translated into acting with the boundary operator, right? So if we now follow this chain of reasoning backwards, we can take this boundary operator and translate it into an action of Q inside a P form defining the offshore amplitude. And doing that, we can show that the BB master equation, that the geometric BB master equation translates in what we call the main identity for the string field theory vertices. And that is already a concrete algebraic statement at the level of these vertices, V0n. And it can be phrased as follows: V0n acting with Q on all the insertions of V0n, of course, with the appropriate signs, right? So Q is degree odd, so we need to pay attention to the signs when we pass it around individual insertions. So this should be thought of as corresponding to this term of the geometric BB master equation. So now we have to also represent the operation of sewing the surfaces through punctures, right? And now we have to perhaps I should have also explained the sum over R here. So of course the particular diagram which I drew on the previous board was just making a special choice of the number of punctures which go to one of these spheres into which I was decomposing the original sphere, right? So, but then of course I have to sum over all possible decompositions R. So this is precisely corresponding to the sum over R here, right? So perhaps that was obvious, but I said it nonetheless. So then I have the same sum over this index R. Then I will have a sum which I will explain in a moment. Then I will have a sum over this complete set of states. And this complete set of states is exactly something which I will use again to represent this operation of sewing the two surfaces along these disk-like regions around the punctures. And then also, finally, I need to explain the sum. So I also need to sum over all possible ways of distributing the individual functions, either into the sphere on the left-hand side of the diagram or the sphere on the right-hand side diagram. I basically need to sum over all possible configuration. So this is precisely the sum here. Okay, so schematically, this is like one set I1 I r minus 1, and if I take the union of this set with I r dot I n, that needs to correspond to the set 1 to n, right? And I'm summing over all possible, disjoint decomposition of this set into two parts. So this is the main identity. So that is already a full algebraic statement. So if I test this equation, on some arbitrary states in my string Hilbert space, I'm in principle able to rephrase this as a set of algebraic equations which these vertices need to satisfy. And again, I can formulate the same sort of recursion as I did with the BE master equation, and to solve this. So just before we make a short break, let me actually talk about one more piece of this chain of equivalences which I've been discussing. So yeah, at each point, just it is good to go back and remember the main statement to what let's say this main identity is equivalent to, and that is the requirement that we are covering the space of 0 and exactly once. So we're just now trying to see what this means mathematically. And the final piece, or the final equivalence which I will give you, is that this main identity is equivalent to the L-infinity algebra, to what we call the L-infinity algebra of string products. So at this point, these vertices, these are just some maps which take me from n copies of the string Hilbert space to in principle complex numbers, right? So with these string products, the idea is to represent this map v0n phi1 phi n in terms of this non-degenerate bilinear form omega, which was already used to write the kinetic term of the action, and some new maps, which this time take you from n-1 copies of the string Hilbert space and give you another state in the string Hilbert space, which is then overlapped with this final insertion which goes into the computation of the amplitude. And these maps are Ln, or Ln-1. So as I said, this should be thought of, Ln should be thought of as a map from the n copies of the co-string Hilbert space.
Linear map.
It's a linear map. Okay, so let's talk about its properties. It's a linear map. It's a map which needs to be totally symmetric in its arguments, right? But then, of course, we also know that the amplitude needs to be totally symmetric in all of the arguments, right, including this puncture here. So that map needs to be graded symmetric and also graded cyclic. With respect to omega. So if you combine these two properties, that Ln is graded symmetric with respect to permutation of the punctures which go inside, and also the graded cyclicity, right, of this map with respect to symplectic from omega, you recover precisely the total graded symmetry of the vertex with respect to all the punctures, right? So then you can finally think about, given these properties, what is the corresponding statement, what is the corresponding algebraic statement at the level of these products ln, which would be equivalent to the main identity. And the answer is that these are precisely what we call the L-infinity relations. And the result, there will be a final term where the Q acts on the final puncture, so let me just not write it. And then on the right hand side, I will have some nested products. Where this sum here is again this complicated sum over these i's, so that we get this disjoint union of this set 1 plus 1. So let me just not write it. Okay. Yeah. So yeah, again, as I was saying, it's good to go back. I mean, what we derive here is that the statement that that the L-infinity algebra of the string product is precisely equivalent to the requirement that the Feynman diagram decomposition, that the amplitude can be computed by a Feynman diagram decomposition with respect to the Feynman rules, which are derived from the vertices of the SFT action. So let me just write down. Actually, let me stop here and have a short break.
Okay.
Yes.
It's 11:20. Maybe let's take a break for 12 minutes, or no, it's 24. Yeah, let's reconvene at like 11:25.
It's 11:12 now. 11:12.
Yeah.